to the third day of the ZK University, or maybe your third or fourth talk. My name is Drew Stone. I'm the founder of Webb. I'll be talking today about mixers, bridges, and private interoperable applications using zero knowledge. Here, there are some links here. You could see some of what we've built, some of the documentation of what we're working on, and my email as well if you want to reach out and talk about anything that has been in this talk and about what we're doing. Some of the topics we're going to cover today are a bit of background on what we need to talk about mixers, bridges, and these zero knowledge applications. So we'll start with a background. Hopefully you have learned a bit so far in the previous classes and maybe in your outside education in the ecosystem. We're going to start with some high-level discussion about all of these topics, so nothing will be hopefully too technical. We'll start with hash functions. Then we'll show how we use these hash functions to build Merkle trees, how we leverage Merkle trees to design different types of zero-knowledge protocols, such as mixers. We'll then generalize these protocols to support more interesting types of functionality, which will allow us to build bridges and build applications on top of these types of systems. So without ado, we'll get it started. So the first thing we need, the first primitive that's sort of required for building up this tool chain are hash functions. So if you're not familiar with a hash function, it's just a method of compressing strings. You could think of it as arbitrary length bit strings that we want to compress to some number of bits, say n bits. We use these hash functions. We take messages, which are inputs to these functions, and we get a digest or a hash as an output to these functions. The reason we want to do this is it takes a large amount of data and it turns, it creates some short representation of it. We usually want these hash functions to be one way, which means it's very difficult for you to go in the reverse direction. You can't take a hash or a digest and go backwards. But there's a bunch of properties that you might use hash functions for that don't rely on cryptography, such as adding redundancy and so on. Certainly for cryptographic applications, we like that digest hide structure from the messages because of that one-way property. A lot of this information was also taken from these slides by Shai. So if you're interested in sort of more information about these hash functions and some preliminary cryptographic knowledge, you can check out this PowerPoint or find a lot of books online. Some examples of how we use hash functions in the wild are, say, signing messages. Instead of signing a message, you might sign the hash of a message so that you sign a succinct piece of data, but you could prove to someone in the future, if they have access to this hash function and this signing algorithm, of sort of verifying your signature. We might create a message authentication code by hashing some specific data together. We might be using hashes to create what are called commitments, which might be used in commit and reveal protocols, where we might commit to, say, a value in a game or a lottery, and in the future we'll have to reveal this hash. And so the one-way property makes commitments nice because you can commit to values and nobody will know what value you committed to because it's not easy to reverse this hash function. But then in the future you could very quickly prove, by revealing the message, that you committed to a value in the past. And there's a few other, applications that we use hash functions for, and certainly this is not an exhaustive list. Perhaps one of the more interesting ones that you will become familiar with throughout this set of courses is so to how we use hash functions to remove interaction between interactive parties in a protocol, such as a zero-knowledge protocol. So instead of having, say, two parties interact with one another to send data, to each other, send challenges back and respond against those challenges, we can use certain cryptographic hash functions. They allow us to remove the need for interaction, which is quite an interesting property. For our applications, some of the things that we kind of care about are collision resistance. So it's hard to find two messages for which their hashes are the same. And we care that these hash functions are one way. So given an output of a hash, it's very hard to find the input that created that output. These two properties are useful for commitments, and certainly for zero knowledge, as if we were to talk about a more lower level application, we would care about removing interaction as well. So with hash functions, we can now talk about what Merkle trees are. Hopefully this isn't a new concept for the people here, but Merkle tree is a binary tree data structure where we build it using some set of data. We build it up by taking pairs of the leaves, pairs of children, or pairs of siblings. We hash them together. So in order to build the Merkle root, which is what we call the top element of the Merkle tree, we're going to take successive pairs of data, and T3 would be the hash of D0 and D1. And we would do this repeatedly, and we would continue to do this at each layer until there's only one element left. This is always going to be the case because we're building a binary tree. So if we fill this binary tree, there will always be, one last layer where we will hash the elements to create a root. This root is really nice because it effectively accumulates all the data into a pretty succinct representation. It accumulates a large amount of data into one hash. And in the future, if I wanted to prove to you that a piece of data is accumulated in this Merkle root, I can hash certain pieces of data, such as like this element and this element and this element together in stages, and I can rebuild this root. And so something nice about verifying data within a Merkle tree is you can do so with logarithmic number of hashes. I can take D3, and in order to prove to you that it's in T0, I provide D2 so you can hash it to get T4, and I provide T3 so you can hash it and get T1, and I provide T2 so you can rebuild the root. And if that rebuilds successfully, then it's extremely hard to fool the fact that that is true because of the collision resistant property. Cool. So now we can take a brief detour. This might be redundant from what you have learned in previous courses, but let's just recap what a zero-knowledge protocol is. It's a protocol involving a prover and a verifier, and it enables a prover to prove to a verifier some statement without revealing any information they might want to keep private. So if we wanted to prove that a number n is the form of a product of two prime numbers, we can do that. We can prove that someone knows p and q such that n equals p and q. We can prove that someone knows x such that g of x mod p is y. We can prove arbitrary mathematical statements, especially over certain other algebraic structures like prime fields. We might be able to, we can definitely prove that someone knows, the preimage of a hash for a public hash function and the parameter d, and so on. We can make arbitrarily complex statements that we would like to prove, such as proving to a verifier that some element is accumulated in a Merkle root without disclosing what that element is and what the path is in the Merkle tree. And so this would effectively allow someone to prove that any element di is inside T0. I just want to prove to you that I know the preimage of some piece of data here. Say every piece of data here is the hash of some other piece of data. I want to prove to you that its preimage is inside T0. And we can do that. We can do that with zero-knowledge protocols. That's going to start to look quite similar to the type of protocol we will want to build. Now, there's a bit of practical terminology that I like to use, certainly building these types of systems and building applications, so we can cover a bit of that now. We say that these protocols have public inputs and private inputs. We can obviously write a protocol that has only private inputs or only public inputs. It just comes down to what it is that you want to keep private and or public. Private inputs are obviously, by their name, the inputs we want to keep private. We don't want the world to know. We take both these public and private inputs and we generate a zero-knowledge proof from them using, open source software today. This is something that, there exist APIs for building these types of programs, and we provide these inputs to build proofs for them. We verify proofs using the zero-knowledge proof that we generated, in the previous description, and the public inputs. So if there's no public inputs, then you would just verify a proof for a zero-knowledge circuit. If there were public inputs, these APIs usually require you to pass those public inputs in. And you might be asking, why would we want public inputs? What if everything is meant to be private? And that's fine. But something that's quite nice is that we can use smart contracts to fix these public inputs in a trustless way. So we might want to conduct a lottery, and we might want to verify some, piece of information that will go into that lottery in a public way. We can fix this public input in a smart contract, and we wouldn't have to worry that at the verification stage some other value is being input into this circuit. Very easily can write a smart contract that forces some value into the public input portion of a verifier. For our purposes, we might, and we're going to put the Merkle root of these Merkle trees as public inputs to the circuit because they are public, and we want to prove some property about data within the Merkle tree. And so we're going to use the root as a public input. So with that knowledge, we can now talk about mixers, mixers and coin joins. And these are applications that we build using zero-knowledge protocols and Merkle trees for assets, for transferring assets to clean addresses or different addresses in hopes of creating some greater amount of anonymity than currently exists on these public blockchains. So a mixer is a cryptocurrency system for anonymizing asset holdings and transfers through some obfuscation mechanism. You might be familiar with the coin join transaction on Bitcoin or Tornado Cash protocol on Ethereum, or hopefully you might become more familiar with Webb Protocol in the future, which is one of the first mixers built for Polkadot, and the first zero-knowledge based bridge between different types of networks in this same family. And we'll talk more about that soon. And the main way that these systems provide and grow privacy is by pooling transactions together, pooling amounts of these transactions together, and providing privacy when people withdraw from these pools. So the first example we can look at is a coin join, which is a type of transaction that exists on Bitcoins or any UTXO-based blockchain. So without coin join, we might have a system where, there's 4 people, Alice, Bob, Carol, and Ted, they want to send transactions between each other. And separately, these transactions would be public on the Bitcoin blockchain. And the output amounts would be public, the change amounts would be public, and so on. One way we can imagine adding privacy to this system is by combining Alice and Bob's transactions into one, called the CoinJoin transaction, so that they can send Carol and Ted the money that they intend, but the amounts that they're sending would potentially be up to question by whoever's observing the system. It's not necessarily the case that Alice is only sending money to Carol. She might be sending money to Carol and Ted, and same with Bob within this CoinJoin transaction. So you could join transactions of different amounts, potentially also even similar amounts, and then send them to arbitrarily many addresses, which provides a nice obfuscation mechanism, on face value. We're going to extend this type of mechanism in a smart contract. We're going to extend it by creating a smart contract that maintains a Merkle tree on chain. And the system will work such that when people want to deposit money into this pool, they're also going to add an element to the Merkle tree. And so the protocol sketch that we can start with is that each user who wants to deposit first generate some set of random secrets. These are usually elements on the prime field for which the zero knowledge system is built on top of. And we're also going to compute the hash of these secrets. We're going to call the secrets S and the commitment C. Once the user has a commitment, they can deposit the assets into the smart contract and insert C as a parameter to this function, in effect inserting C into a Merkle tree with Merkle root R after insertion. We can imagine protocols where there's variable deposit sizes, but we're going to start with the fixed amount deposit because for obfuscation purposes, if all the deposits are of the same amount, then all the withdrawals are also of the same amount. And therefore, when someone withdraws the assets, it's not clear which deposit the withdrawal, is linked to. And that's the primary way that we get privacy through obfuscation. So as was mentioned, when a user wishes to withdraw their assets, they're going to withdraw this fixed amount of assets, and they're going to do so by submitting a zero-knowledge proof that proves some statements, such as the hash of the secrets is the commitment, and they're going to prove that the commitment is in a Merkle tree with a certain root, say R. And the user's only able to prove this. Obviously, they want to keep the commitment. Private. The reason for this is if they pass the commitment as a public input, then anyone observing the blockchain could see which deposit was theirs. So this will be a private input, and the secrets will also be a private input. The path that allows them to recreate the Merkle root will be a private input, and the only public input will actually just be this Merkle root R. And so as was mentioned, we start with fixed size deposits. That allows all withdrawals to look the same. They look like the same amount, and the zero knowledge proof hides all the private data we want. It hides the commitment, the pre-image of the commitment, and the data required to prove membership of that commitment in the Merkle tree. And so this is sort of, I'm stressing that the root is the public input because we built this Merkle tree on chain. So we can push the Merkle root of the Merkle tree root on the smart contract directly to the verifier because our verifier is also going to be on chain. So this is not a piece of data that any user can tamper with. They can only prove they know an element in the tree if they in fact inserted an element into the tree. We can extend the mechanism to support arbitrary deposit sizes and withdrawals. We can do so by making our commitment slightly more complex. So we might still sample a bunch of secrets, but we might now choose a deposit amount, call it A, and then take the hash of that, and that'll become our commitment that we put in the tree. Now the protocol will look like, we'll deposit A amount of tokens into the contract, which will verify our balance, and we'll insert C into the Merkle tree. We'll sample a bunch of new secrets such that we can effectively spend some of this asset. Say A, we can spend some amount A of this asset, or some, smaller amount of it. And we're going to run through this sketch right here. We're going to create a new commitment which commits to some amount of the asset A double prime and S double prime. This is, strictly less than A. Then we're going to withdraw, the other side of that difference and insert a new commitment into the tree by submitting a zero-knowledge proof that does a bunch of things. First, we need to verify that we own, or we know we have knowledge of a commitment whose amount is A, because we're going to split A into two different, actions. We're going to prove that that commitment is in the Merkle tree with some root R. We're going to prove that the amount we're withdrawing, which is A prime, plus the amount that we are changing our note into, which is A double prime, equals A, which is taken from the commitment we're spending. And in doing so, we're going to allow ourselves to add a new commitment to the tree, C double prime, which commits to the smaller A double prime value. And we're going to submit a bunch of proofs of knowledge that all the commitments are well-formed. Well-formed commitment is one like this. We also are going to prove that, C double prime is well-formed and that there's some secrets and some amount, and so on. Now you might be asking yourself, if I get a proof to verify once, what stops me from using that proof multiple times? This comes down to how we engineer the smart contract application. And certainly this is probably the most important part outside of the design of the zero-knowledge circuit. So the most important thing is really preventing double withdrawing, or else anyone could steal all the money that gets put into this pool. The way we do this is with yet another set of constraints on our zero-knowledge program. We are going to require for this type of protocol, for the mixer protocol, that one of our public inputs be a value that is tied directly to the preimage of C, but that exposes no information about C. And we talked about something in the beginning that lets you kind of do this because it has some one-way property around it, and that's a hash function. We're going to take the hash of, say, one element of the secrets. We're going to call that a nullifier, and we're going to expose that nullifier in the process of withdrawing. So put more formally, we choose the hash of one element of the preimage and expose it. We call that exposed element the nullifier. And we add a constraint to our gadget such that when we pass the nullifier into our circuit as a public input, we're going to verify that the nullifier equals the hash of one of the secret values of the commitment, the commitment's preimage. We're going to verify that the hash of them match the nullifier. And the reason we do this is so if this verifies, we're going to store the nullifier in the smart contract in public. And if a user ever tries to withdraw with the same commitment, they're going to compute the same nullifier, and we can stop them. We can basically see that they're using a nullifier that's already been used and we can see this on the smart contract, so we can trustlessly reject it. Cool. And so you've seen in a variety of ways we've built up this system by changing different values and changing different parts of our protocol. We might have added some data to our commitment. We might have created a protocol in which we can spend and split these commitments by their amounts. And finally, you see we can create mechanisms for preventing the double submission of these systems or of these actions by adding yet more data and proving some property about them, and about the public data that we will choose to expose. And we can continue to generalize these types of protocols in a few ways. We could add more arbitrary data to these commitments. So maybe instead of the amounts, we also add an asset identifier, and then we can get a mixer that supports multiple assets at once. And we can add arbitrary rules to these smart contracts upon insertion. We can say that you can only append an element to the Merkle tree if you possess a valid NFT or a valid identity or pay a certain fee, and so on. This is sort of like an area in which your imagination is powerful, because you can create applications for pretty much anything. It's all about sort of what data you want to verify, what data do you want to prevent people from being able to put in, or who you might want to prevent from being able to put data in these trees. And so with that, introduction to mixers, we can talk about building bridges out of this same mechanism by generalizing one part of our protocol. So when we talk about making mixers interoperable, we're asking the following question: how do we prove properties about data in one of many Merkle trees, or the smart contracts that they live on? We may want to store the same or even different data in different trees. We may deploy these smart contracts to different chains, and we may enforce different rules over these deployments for the different communities that might be using them. And the main generalization that we take advantage of here is by augmenting the membership proof. So before, we were proving that an element is in a Merkle tree by proving that it's accumulated in its Merkle root. And instead, here we're going to prove that a piece of data is in one of many Merkle trees by proving that the Merkle root we create in the circuit is in a set of Merkle roots. Primarily all the Merkle roots and Merkle trees we want to connect together in this interoperable and bridged system. So how do we do this? We start by augmenting our commitment with some metadata about the chain that the membership proof is meant to be submitted on. If our set of roots is something like this, it's R1 through Rn, we can take a commitment to Ri and use its identifier as part of our hash. And now our commitments for, the previous mixer applications we talked about would look something like this. They would have I, the amount, secrets, or just without the amount if we were dealing with fixed deposit bridges. And the proof you're going to send to the verifier is that a commitment in one of many of these Merkle trees with these Merkle roots, where the index of the target root is a public input. And this primarily is used for preventing double spending, so that you can't submit a proof on multiple chains that verifies. You can only submit it where I actually is. And this allows us to take certain actions across chain, like transferring assets. Inside of the zero knowledge circuit, we are going to recompute the commitment with the preimage data and the public identifier. We're going to pass in a private Merkle path for the target Merkle root that we want to recompute. And then we're going to do a one of many set membership verifications to prove that that computed root is inside of this set R. And this set R is, a tricky part because it needs to be kept up to date on every smart contract that it exists on in order for people to submit proofs to it, to these smart contracts. So like when the system on chain 1 gets a new insertion, all the other chains need to somehow learn about this. And that's a topic for another class, but if you're confused a bit, it's totally warranted. This set R needs to be updated by some external third-party system. And we won't talk a lot about what those are. They can be trusted solutions, they can be trustless solutions. But we'll say that that R updates, through an oracle, and it updates trustlessly for the sake of our discussion. And so now we've looked at how to augment a membership proof to support an interoperable application, one that looks very similar to our mixer, where we want to provide privacy for different assets. But we can also generalize the purpose of these applications by just putting different data into these systems. So recapping, for an interoperable asset mixer, we need the index in the commitments in order to prevent double spending. If there's no data constraining the location where the proof is being verified, then the proofs can be verified everywhere. And that might mean that someone can take one proof, withdraw it on all the other chains, and withdraw more assets than they've deposited. We leave, proving this. This is part of the exercises for this week's, for this lecture specifically, to show your understanding of why we might need the index in these commitments. For the asset mixer, we can talk about the type of zero-knowledge relation. If you're curious, we'll go through it a little quickly, but this is sort of the formalization that one might see in a paper. So for the asset mixer, what's happening? We need to find some statement X and witness pair that satisfy this relation. That's how we define it. And the way that this pair, X and W need to be are defined here. They are in the following. The witness is all the private data that we need to prove this statement X. We take the witness to be some random data row or R and row. We take it to be the nullifier and the path of this commitment. What is this commitment? We take the commitment to be the hash of the identifier of the chain, R, row, and the nullifier. We have an algorithm that rebuilds a Merkle root, a computed Merkle root, from this commitment using the path and the hash function. And the statement we want to verify is that this Merkle root is inside of a set of Merkle roots, R, and that there's some serial number which is equal to the hash of the nullifier. And we take this serial number to be a public input. That's the piece of data we're going to store in the smart contract to prevent, proofs from successfully withdrawing funds more than once. This index I prevents proofs from verifying on multiple locations. And this serial number prevents proofs from verifying more than once on the same location. And so we have an interoperable asset mixer now. For other types of applications, we can build general just communities or membership sets without any transferring of assets. So we might want to create a multi-chain NFT community where, given a set of bridged Merkle trees on multiple chains, we can add rules so that you can only add elements to these Merkle trees if you possess a certain NFT. And that means we can build an interoperable membership set around NFTs and then applications where you might be able to prove your membership inside of this community and take certain actions from it. So being able to prove you're in this set of Merkle trees because it effectively proxies a proof that you own this NFT without proving who you are. So you might be able to take an action on behalf of a group or a community privately and on any chain. And there's a mechanism that allows you to build applications that, allow the participants of these trees to vote on certain things and signal certain topics. It's called semaphores. And this system is built very similarly to a mixer, except that it has different actions. So instead of transferring, or instead of mixing assets, it allows people to do anonymous signaling. And we can take this system and extend it in the same manner we did with our mixer to make it interoperable over a bunch of Merkle trees. So I would definitely recommend checking out this link below. This is a super cool project. And something in particular that we at Webb have done is build this in an interoperable fashion so that you can create these membership sets from many, many chains and then run polls on, wherever it's cheaper to run this, an on-chain poll. But yeah, that's it. As always, there's lots of different applications you can leverage these types of techniques to build, and would certainly love to hear from you guys as far as, the types of applications or ideas you might have. And if you want to work with us at Webb to help realize these applications, my email's right there. You can certainly reach out to me, and there'll be some potential exercises in the from the class that will, hopefully get you thinking about what you can build with this type of interoperable stack. But thanks so much for everyone that made it this far, and I hope you learned something. I hope it was informative. Take care, and good luck in your learnings.